All right, so I'm going to be walking through ChipWhisperer Side Channel Analysis 101, Lab 3.3, which is a differential power analysis attack on a firmware AES implementation. This lab splits into a hardware side, where we capture traces from the target, and a main notebook, where we use those traces to recover the AES 128 key with a DPA script. The goal is to show that even though the AES key never leaves the device directly, the device's power consumption leaks enough information for us to infer it. In this lab, the attack targets the AES S-box stage and turns the small differences in power into key guesses. So the big idea here is that power depends on the data a chip is processing. So if the data changes, the power traces change too. The notebook explicitly assumes there is a consistent relationship between bits on the data bus and the device's power consumption. For AES, the useful intermediate value is the S-box output after combining a known plaintext byte with an unknown key byte. Once again, the useful intermediate value is the S-box output after combining a known plain text byte with an unknown key byte. If I can guess a key byte, compute that intermediate, and predict one bit of it, I can sort traces into two buckets and check whether the real hardware behavior agrees with that guess. This lab is structured around two notebooks with one attack pipeline. The hardware notebook captures the data, and the main notebook consumes trace array and text in array to run the analysis. That separation is nice because main does not care whether the traces come from a real board, a simulator, or pre-recorded data. As long as the arrays have the expected shape and content, the analysis code stays the same. On the hardware side, the notebook needs to know what capture platform and target configuration we're using before anything else happens. In the deck, this run is set up around the CW Nano with scope set equal to CW Nano, platform set equal to CW Nano. Crypto target is set equal to tiny AES 128C. And the tutorial materials also describe selecting the platform and building simple serial AES firmware before flashing it to the board. Once the firmware is flashed, the target is running a known AES implementation that we can repeatedly simulate with random plain text. And so once again, once the firmware is flashed, the target is running a known AES implementation that we can repeatedly simulate with random plain text. That gives us a controlled victim where the secret key stays fixed while the input changes across captures. This is the capture loop, and it's the bridge between theory and actual measurements. For each iteration, the setup triggers an encryption, records the power waveform, stores that waveform in trace array, and stores the corresponding plaintext in text in array. The lab expects 2,500 traces at this stage, and later cells assert that length before continuing. So the important takeaway here is that every trace is paired with the plaintext that generated it, and that pairing is what makes the hypothetical leakage model possible. At the handoff point, main doesn't need live hardware access anymore. It just needs the captured trace array and text in array. And the notebook even tells us to paste the capture code from the hardware or simulated branch into the AES Power Watcher section. And there's also a sanity check here. The notebook asserts the function len traceArray equals to 2500 and prints an OK message before moving on. If that step fails, the rest of the DPA flow won't make sense because the analysis assumes the capture stage is completely correct. Now we get into the actual attack. For one sub-key byte at a time, we try all 256 possible guesses from 0x00 to 0xFF. Compute a hypothetical SBox output for each trace using SBox input XOR guess, and then inspect one predicted output bit to split traces into a bit equals 1 group and a bit equals 0 group. After that, we average each group point by point using NumPy with axis set equal to 0, subtract the two average traces, take the absolute value, and record the maximum difference. The correct guess should produce a notably larger peak than the wrong guesses because it aligns the group with the device's real internal computation. So once again, the correct guess should produce a noticeably larger peak than the wrong guesses because it aligns the grouping with the device's real internal computation. One useful checkpoint in the notebook is byte 0 because the lab tells us the correct value is 0x2b for validation. The example in the notebook shows the maximum difference for 0-2b standing out above nearby wrong guesses, which is how you know your implementation is behaving correctly. From there, the same idea scales to all 16 AES key bytes. The notebook wraps the byte attack in an outer loop over subkeys, ranks all 256 guesses with np.argsort, and builds up the full known AES key 1 byte at a time. If the attack doesn't immediately recover every byte, that's normal in this lab. The notebook discusses ghost peaks, where an incorrect key guess creates a strong spike that can outrank the true key unless you look more carefully. The suggested fixes are to capture more traces, try different target bits of the SBox output, or window the traces so you only score the part of the waveform where the meaningful peaks occur. The notebook also gives us an example known key, which is shown as in the next slide. So we can validate whether our ranking and window logic are actually converging on truth. Actually, it was the previous slide. This is the known key for validation, starting with 2B, 7E, 15, ending with 3C. This lab is the moment where side channel analysis stops feeling abstract. With enough traces and a simple statistical script, one leaked bit at a time is enough to unravel the entire 128-bit AES key. So let's go ahead and get started with the lab. First things first, I'm going to go ahead and navigate into our directory where we have the ChipWhisperer documentation in the laboratory. We're going to launch our Jupyter Notebook server. But first, we're going to activate, I think we have a Python environment. The lab is located in the Jupyter folder in courses in SCA101, lab 3.3. We're going to open the main. We're going to open the hardware versions of this notebook. So this notebook walks us through performing the DPA attack, which stands for Differential Power Analysis. And that attack is being performed on a firmware implementation of AES 128 using ChipWhisperer and Python in Jupyter Notebooks. So let's go ahead and get started. So we're going to start in the main notebook first. In the previous lab, we saw how a single bit of information can be used to recover an entire byte of the AES key. Remember, this works due to the S box being present in the data flow we are attacking. Now, remember that an S box is a nonlinear substitution lookup table used to obscure the relationship between the key and ciphertext. It takes an 8-bit input and maps it to an 8-bit output, preventing attackers from using simple mathematical equations to break the encryption. The AES S box isn't random. It's generated using 2 strict mathematical operations in a Galois field. Multiplicative inverse. It calculates the multiplicative inverse of the input byte. The Ringdale S box is a substitution box lookup table used in the Ringdale cipher, on which the AES cryptographic algorithm is used. First, you will need to select which hardware setup you have. You need to select a scope type, a platform, crypto target. So let's set that up here. The CW Nano, Tiny AES, and I believe this is SSVer 2.1. So I'm going to go ahead and plug in my device. Here I have the CW Nano. I'm going to plug it in, make sure it powers on. We run this run block here. Our ChipWhisperer has been found. We're going to run the make command here, which builds the platform, crypto target, and simple serial protocol. And here we have a build log. It looks like it completed successfully. Now we're going to program the target with our firmware. So for this tutorial, we'll need to capture around 2,500 traces. Let's go ahead and take a look at the. All right, so right now we're running the hardware notebook. So we selected the hardware plus the target constraints. We have built and flashed the AES firmware. Now we need to create scope and target objects, which will be here in this block. This is the cell that imports ChipWhisperer and calls scope and target. So after this, we're going to move into the main notebook. So this last cell typically is taking the list of individual trace objects collected in the main capture loop and converts them into a two-dimensional NumPy array named trace array, which we can see here, trace array. It's building a matching text in array from the plain text associated with each trace. The keys are recorded during capture. For fixed key firmware, these are all the same. This is mainly for validation and for the simulated path. All right, we have captured all the traces. So now we're going to switch to the main notebook to actually break the key using dynamic power analysis. So the learning outcomes for this lab will be using a power measurement to validate a possible device model, detecting the value of a single bit using power measurement, and breaking AES using the classic DPA attack. Before we continue, check that we've done the following tutorials, which we've done in the previous episodes. No need to remember the complex model from before. We can just instead jump right into the AES model, copy your AES model you developed in the previous lab below and run it. All right, so we are in the main notebook, which runs the actual DPA. The first thing we need to do is pick whether our traces come from real hardware or from a simulated data set. I'm selecting hardware here, and the notebook uses that to decide which helper notebook to run to populate the trace arrays. All right, you can verify the model works by running the following blocks, just like last time. Simple test vectors. If you get the check mark printed, all okay, then we're good to move on. So this cell runs a couple of simple test vectors through AES internal. The asserts check that AES internal is equal to 0x1b, that this first one's equal to 0x1b, and the second one is equal to 0x26. If both checks pass, the notebook prints OK to continue, confirming that our leakage model is wired up correctly. All right, here is the AES Power Watcher. The next step is to send random data to the device and observe the power consumption during the encryption. The idea is that we use a capture loop like this, where we have print, we're printing the scope, we have a for loop for I in T range, N, description is equal to power, capturing trace. We have key and text set equal to ktp.next, which manually creates a key and text pair. Trace is set equal to capture trace, where we input the scope, target, text, and key. If trace is none, then we continue. We append each new trace, and then we plot the trace. And then after that loop, we convert traces to NumPy arrays by setting the trace array equal to NumPy as array. Depending what you are using, you can complete this either by capturing new traces from a physical device, reading pre-recorded data from a file. So here I'm doing hardware. Inside those notebooks, you should get some code to copy. All right, so before attacking, we plot a few of the actual measured traces from tracearray. This lets us see where the AES operation lives on the timeline and where the largest data-dependent swings occur. Later, we get into different traces. We'll want our scope, our scoring window to focus on this region. Perform capture, resulting in trace array and text in array of two 500 traces. We have assert len trace array set equal to 2500, print OK to continue. What do we need to implement? What do we need to implement in this cell block? If you're doing the hardware path, the cell should look conceptually like this. Well, I'm looking at the solutions. Oh, no, I'm not. All right, so all right, let's start implementing some stuff here. So we're gonna need NumPy, import NumPy for array conversion and trange for a progress bar. So then we're gonna have to initialize traces, set that equal to, unless traces was initialized already. It may have been in the other notebook. Let me see. All right, so we set traces equal to empty brackets. This list will hold each successful trace. Keep capturing until we have 2,500 valid traces. With trange 2,500, set the description equal to capturing traces as pbar, while len of the traces is less than 2,500. We're going to get the next key in plain text pair. Key and text is equal to KTP next. And we're going to capture one power trace by initializing trace and setting it equal to CW capture trace with the scope, target, text, and key. Now, if the capture fails, try again without advancing the progress bar. Save the valid trace and update the progress bar. Traces, append trace, progress bar is updated. Then we're going to convert trace objects into NumPy arrays for analysis later. We're going to set trace array equal to NP AS array. Then we set this text in array equal to np as array trace.textin for trace and traces. Then we have known key trace.key for trace and traces. And then this is going to confirm we have the required number of traces. ktp.next. Is it because I don't have time? Or I didn't say KTP, set KTP up here? Okay. Set up KTP, which stands for key/text pair generator. Just like that. It's still not working. Import ChipWhisperer as CW. Scope is not defined. Why are all these errors occurring? Scope arm. The error means the hardware setup cell has not been run yet. Scope and probably target are supposed to be created in hardware notebook, not in the main notebook loop capture. Okay, so I see. So I'm gonna go ahead and add some cells here from the hardware lab. I neglected to do that. I'm gonna go ahead and just reset the kernel and unplug the device. Plug it back in. And we're just going to put these cells in the main notebook. For some reason, I thought they would carry over, but they're different kernels, and we didn't specify them to share the kernel, so that should fix it. I wonder if I need to also call this. I feel like I might need to, so. Maybe not. Let's just go ahead and test it out. Huh. Maybe I need to add this in there. So let's go back, clear all outputs of the cells, kernel, restart, disconnect the device. We're going to do this one more time. All right, we got the device reconnected. All right. That's strange. Oh, okay. We forgot to include this. All right. Everything should work now. Okay. Let's try it again. There we go. So as the progress bar advances, the notebook is repeatedly triggering the device to perform AES encryptions and recording the analog power waveform for each encryption, plus the associated plaintext and key, to build a dataset that we'll later attack with dynamic power analysis. Each step of the progress bar corresponds to one trace being captured. The host sends a plaintext, and often a fixed key, to the target, arms the scope, lets the target run that AES firmware, and then reads back sampled power signal from the ChipWhisperer analog to digital converter. So this is being done in the for loop wrapped by the TQDM, so the bar reflects how many encryption and traces have been collected so far. Okay, so now we're going to go ahead and run this next block, run the next one, and there we go. Let's capture these traces. So this cell is our data collection engine. So right now, this talks to our ChipWhisperer 2,500 times, each time requesting an AES encryption, collecting the corresponding power trace, and finally, packaging everything into NumPy arrays for later DPA analysis. This is automating capture of many power traces from the target running AES under a fixed key and varying plain text, using KTP basic to generate key plain text pairs. And it's filtering out all the failed captures. It's showing a live progress bar, as you can see, and converting the ChipWhisperer trace objects into plain NumPy arrays, which consist of the trace array, text in array, and the known keys. The later cells will use this information for dynamic power analysis attacks. So here the KTP equals cw.ktp.basic is creating a new key pair, a new key text pair, and by default it holds the key constant and produces random plain text, which is typically the pattern you need for dynamic power analysis on AES. The traces list will store each successfully captured trace object. Each trace bundles the waveform, plaintext, ciphertext, and key. So inside this while loop, the key and text is set equal to the next pair for a key plaintext. This trace is set equal to cw.captureTrace. This sends that key in plaintext to the device, triggers an AES encryption, and records power consumption waveform until the scope capture completes. If something goes wrong, it skips updating the progress bar and retries. Otherwise, it appends a trace and advances the bar by 1. So after collecting 2,500 successful traces, we get this OK to continue. So now we want to see what the data is going to look like. So we can see what the data looks like by calling the CW plot trace array 0. So that's one trace. Now we can see what it looks like compared with another trace. And let's see what it looks like compared with another trace. Yeah, so as you can see here is basically just several different traces. So we know it's working. So we've got data, and what about the format of the input data? Each entry is a vector of 16 unsigned bytes, values in the range 0 to 255. This matches the AES block size of 128 bits, which is equal to 16 bytes. So each row is a single plaintext block. Just to experiment a little bit more with it. 1, 2, 3, 4, 5, 6, 7, 8, 9. So the printed text in array rows show that each input is a 16-byte vector, so the format strongly suggests standard 128-bit AES plaintext blocks. Each entry is a vector of 16 unsigned bytes. In the DPA model for this lab, you then select 1 byte index, and for each key guess run, input byte is equal to text in array trace index byte to attack. Hypothetical leakage is equal to AES internal input byte and guess. So the format tells you that you're in a classic fixed key random 16-byte plain text DPA setup, and that each trace is aligned with one 16-byte AES input block, exactly what you need for per byte key guessing on AES 128. If you like, we can walk through choosing byte to attack and implementing the 1 byte DPA loop using this text in array next. All right, so next we have AES guesser, 1 byte. The attack now needs a way of splitting traces into 2 groups. Depending on the state of a bit in our guessed value, we're going to start easy by guessing a single byte of the AES key at a time. To start with, define the number of traces and number of points in each trace. You can use the following example code. Just run this block. If you remember from the slides, our algorithm looks like this. 4 key byte guess value in 0 to 255, 1 and 0 lists are set to empty. And for each trace index and the number of traces, set the input byte equal to text in array of the trace index and the byte to attack. Get a hypothetical leakage list. The important thing here is access is equal to 0, which does an average, so the resulting array is done across all traces. All right. So for each possible key byte guess, between 0 and 255, store the max. Difference between power groups. Index is equivalent to key guess. Guessed byte is equal to 0. Attack byte 0 of the AES key, which is the first state byte. Loop over all 256 possible values for this key byte. For guess in range 0 and 256, and 0 list. One list will be traces where the selected leakage bit is set equal to 1. 0 list will be the list where traces that are selected will be set equal to 0. Now we want to iterate over all captured traces. For trace index in the range of number of traces, we want to get the hypothetical leakage for this trace under the current key guess. AES internal method receives the guess in the input byte, models subbytes on 1 byte, and it applies SBox to plain text XORed by the key guess. Partition traces based on the least significant bit of the hypothetical leakage. Next, we're going to compute the average trace for each group. right. You can use the following general program flow to help you implement the outer loop above. Yep. So these numbers are the score of each key byte hypothesis. The larger the value, the more that guess explains the power trace. So the highest values point to the most likely correct key byte. Each line has the form guessing XX, a candidate value for key byte 0, and hexadecimal. The float is the maximum absolute difference between the average bit set equal to 1 traces and bit set equal to 0 traces for that guess. The float is our distinguishability metric, how strongly that guessed key causes a separation in power consumption when the targeted SBox output bit is 0 versus 1. So we want to look for the largest value in the whole list. Take the corresponding hex guess as the recovered value for key byte 0. So just eyeballing our output, a few of the higher peaks are going to be anything with a 9 here at this third value, or anything with a 0, 1. So like this one. This is one of our peaks. Here's another one. So this attack run is currently telling us that byte 0 of the key is likely 0xE0. Assuming traces are in alignment are good. So these cells down here kind of give you the framework for this entire code block that I was able to run just now. So you've got hint 1, general program flow. Hint number 2 is example of 2 different key guesses. We aren't fully going to give away the code, but you can check the solutions notebook. Here's how you can generate 2 differences. ranking guesses, you'll also want to rank some of your guesses. This will help you identify the most likely value. The best way to do this is to build a list of the maximum difference values for each key. For example, run the following to see it in action. 3102. So it's just telling us which of these values is the largest. Before we move on, you should take a look at various plots of these differences. They will play in something called a ghost peak problem. We're now going to define a function called calculate diffs. Calculate diffs implements our attacks. Try plotting the difference between various bytes. For byte 0, remember 0x2b is the correct value. Zoom in on the plots and see how the correct key should have a much larger difference. Sometimes we get ghost peaks, which are incorrect peaks. So far, we're assuming there is a single best solution for the key. We may need to get fancy and put a threshold whereby we have several candidates for the correct key. For now, let's just plot a handful of examples. You'll notice when we rank the bytes, we just use the maximum value of any peak. There's lots more you could learn from these graphs, such as the location of the peak, or if there are multiple peaks in the graph. But for now, we're just going to keep with AES guesser, all bytes. All right, good job. You've got a single byte and some DPA plots up. Now let's move onward and guess all of the bytes. Doing this requires a little more effort than before. Taking your existing guessing function, you're going to wrap a larger loop around the outside of it, just like this. All right. This block is the full multi-byte dynamic power analysis attack. It runs our difference of means test for every key byte position, ranks all 256 guesses, and builds a 16-byte key guess where keeping all intermediate traces for later analysis, which includes ghost peaks, windowing, among others. The high-level behavior here is that it loops subkey from 0 to 15 for each key byte position and tries all 256 candidate values. For each guess, it calls calculate diffs to get the difference of means trace, bit-based dynamic power analysis, and then records its maximum value as that guess's score. It sorts the 256 scores, picks the largest as the current best guess for that byte, logs the top 5 candidates, and stores all full differences trace in full diff list for later plotting and windowing. max diffs, full diff trace. Keep the entire difference trace so we can analyze and plot the ghost trace, ghost peaks. And we're going to save a copy of all 256 diff traces for this subkey. We're going to rank all 256 guesses by their score in descending order. We're going to call our argsort function. Then we're going to take a high scoring guess as the best current key byte guess. So here we're going to display a message that compares the most likely guess with the known key. We're going to print the top 5 guesses as well. We want to visualize the uncertainty as well as the ghost peaks.
All right, the moment of truth. Let's see if that compiles and runs.
Button on. Whole diffs list. Dot append. There we go. So this script performs a full 16-byte differential power analysis attack on AES 128 implementation using measured power traces. For each key byte position, 0 through 15, the code tries all 256 possible values of that byte. For every guess, it calls calculate diff, where we pass in a guess, a subkey, and bitnum, which partitions traces based on the value of one SBox output bit and computes a difference between the average 1 and 0 over time. The result is a difference of means trace whose peak indicate times where that bit has a strong influence on power consumption. So as it ran, the script prints a summary line such as subkey 10, most likely C2, actually 15. Hopefully the above worked. We're now going a little further to understand how to apply this in case it didn't work right away. Run the following block. Will take a bit of time. After it runs, select a subkey that is either wrong or has very close next best guesses. For example, the following shows the output for subkey 5 is actually wrong.
So all of our subkey guesses are wrong. The correct key byte is not a clear outlier in these scores.
Okay, we're going to get into more efficient attacks later, but for now, let's look at some solutions. Increase the number of traces recorded, change the targeted bit, window the input data. The first one is the brute force option. Now go from 25 to 5,000, or even 10,000 power traces. As you add more data, you may find the problem is reduced, but real ghost peaks may not disappear, so we need to move on to other solutions. Before we begin, we're going to give you a known good DPA attack script we're going to build on. This uses calculate diffs, which was defined earlier. Now run the following block. It'll take a little bit of time. This block should now print some next top guesses. In this case, just the next top 5 guesses, but you can extend it if you wish. It's also keeping a copy of all the different traces. After it runs, select a subkey that is either wrong or has very close next best guesses. For example, the following shows output for subkey 5 is actually wrong. The correct guess has been ranked as an option. Actually, AE, which is right here. You can find the full diff in the full diffs list array. If you index this array, it will give you every guess for a given subkey. For example, full diffs list 5 is the 5th subkey guess output, which would be that one. Using full diffs list and to get your selected subkey, plot the correct key by plotting in green as the last. Plot the correct key by plotting full diffs list n0x correct in green as the last, as in green as the last. Oh, I see green here. Zoom in on the window and you should notice there's a location where the correct peak is higher and the incorrect than the incorrect peaks. If you want to plot all traces, this will get slow. For a given trace, we can do the following. You're indexing past the end of the inner list, at least one of doesn't exist for your data, so Python raises an index error. It's a polygon to use a valid subkey and make sure you're actually attacked.
Zoom in and out on the zoom in on the window, and you should notice there's a location where the correct peak is higher than the incorrect peaks. If you want to plot all the traces, we can do so. You're getting the index error because full diffs list only has one entry. You're trying to index subkey 12, which doesn't exist in your current run. Depending on your hardware, the previous may show a single nice large spike or multiple large spikes. If we have the ghost peak problem, you've probably got multiple spikes. The incorrect peaks may trail behind the correct locations. We can first plot the correct locations by looking at the known key. The following will do that. Something is going on with the subkey. So the peak is highest here. I'm not sure which one is yellow. I think it's this one, AE. Yep. If you want to plot all the traces for a given trace, we can do something like this. See, this is the peak.
See if you can get the correct key to come out for every byte. So I'm not getting the correct key to come out for every byte. Oh, there we go. This ended up being even worse. Doesn't look too good. None of the individual bits gives us a strong enough DPA signal to recover key bytes. Every bit alone leaves all bytes wrong, which is exactly what the lab is setting you up to observe before moving on to correlation power analysis, multi-bit combining. Single-bit DPA on this firmware AES and this trace set has weak leakage, and using just max difference on one bit is not a robust way to recover the key. In this lab, dynamic power analysis is used as a concept demo. You implemented the partitioning by one bit. We computed the difference in traces and saw that some key guesses look better than others. But when you try to push it to full key recovery, we discover it's fragile. Now we've seen how dynamic power analysis attacks can be performed using basic Python scripting. We'll experience much more effective attacks once we look at correlation power analysis attacks, if we want to perform these attacks in practice. The Python code here isn't the most efficient. We'll look at the faster options in later courses. Well, that's a relief, because this was very much a letdown in terms of actually cracking any kind of information. Well, we made it through the lab. That's a success. On to the next one next time.